Swayam Prabha. Digital India. Educated India.
Welcome everybody to NMR spectroscopy problem solving session. Today we're going to look at dye-substituted benzenes, splitting patterns, and also we're going to look at shifts, chemical shifts when you have electron withdrawing groups, electron donating groups. One of the things you could do is just review the benzene chapter and then come back. That would make a lot more sense. But, here we go. Dye-substituted benzenes, that means you have a benzene and you have two groups on them. So this is your benzene, and benzene has got ortho. Benzene can have meta, and dye-substituted benzene can have para. Those are the three possibilities. We are going to look at what would happen if you put an electron withdrawing group, an electron donating group, electron donating group, and electron withdrawing group. So that's what we're going to do today. Of course, you can always put two electron donating groups or two electron withdrawing groups or some combination of that. But this is what we are going to look at. We're going to look at NH2 for your electron donating group, amine. So like an aniline that's substituted, and electron withdrawing group, we are going to use NO2. We are also going to talk about splitting patterns. So benzene has also hydrogens next door on this vinylic carbon, so you can have two hydrogens next to each other, and they will couple. Their spins are going to interact and they will couple, and you will get, let's say this is A and B, a coupling constant, which is quite large for ortho 1, 2 hydrogens here. JAB would be 7 to 10 hertz. Okay. You could have hydrogens that are meta, that means 1, 3. So this is 1, 2. You can have them 1, 3. And there the J, let's say this is C and D, that is good. The coupling constant there, even though this is 1, 2, 3, 4 bonds away, so you do see some long distance coupling here, and this is going to be about 1 to 3 hertz. Now let's look at the para. Will they even split? Because now it's going to be 5 bonds away. Let's say E and F, HF. Will they split 1, 2, 3, 4, 5 bonds away? If you have a very, very powerful, magnet, then you would be able to see the splitting. It's going to be just 0 to 1, but most machines won't show it. Most of the undergraduate labs would have like a 300. So you're basically seeing ortho and meta. Now, another thing that we need to bear in mind is resonance when we come to benzene. That's one of the reasons why all of these hydrogens are not in one spot or one chemical shift. They have different chemical shifts. And we're going to see the reason for that. The main reason, if you would recall in benzene, we talked a lot about resonance. So let me do a resonance with this and with this individually, just to show you where the electron density would be mostly. So if you have an electron donating group, in this case, this group is a resonance donor. That means the electrons actually step into the ring. It's not just a little push along the sigma bonds like if you had inductive donors. This is a resonance donor. So therefore, this is going to come over and put the electron density here. Drawing the resonance structure from here, you would see that you would have a double bond now, and the nitrogen is going to be positive, and you would have a negative charge here. So it's ortho with respect to the amine group. These can then go in. Remember, there are hydrogens here, so if you push this in, someone's got to go, and that would be your pi bond. And you would put that pi bond electron here as a lone pair, and you would get a structure like this, a resonance structure. Okay, all along you can see plus minus would give you a neutral structure, and this is the most stable, this is where it is, but you could have a little bit of a shift. So in terms of chemical shift, you know, when electron density is high, then the chemical shift value goes down. So therefore ortho and para are shielded, and they would have a lower delta ppm value for the chemical shift. Let's see what happens if you had an NO2 group. Okay, so here your electron donating, electron withdrawing group can be ortho, meta, or para to that, and each situation would be different. But if you just had a nitro, this is just to review what could happen with the nitro group inside a ring. So let's say I have a nitro group here. That is going to be electron withdrawing because of all of these very, very electron withdrawing groups pulling electrons off. So that's going to pull this up. So if you have a nitro group, ortho to that, you are going to have a depletion of electrons, positive. So just the opposite of an electron donor group. This is an electron withdrawing group that can do resonance. So it's even more powerful than just an inductive group. So here we have, well, 2 minus, 2 plus. So then therefore, you know, the original structure is also a neutral. So all the molecules are neutral. So ortho is going to be, in this case, de-shielded because you're depleting electron density from that position. Again, if you take your resonance structures, this can swing open, and you can put a positive at this carbon. So then that is going to give you a nitro. A ortho para are shielded for an electron donating group, and ortho para are de-shielded, and you'll have an increase in the chemical shift, delta ppm chemical shift. And as I said before, NH2 is going to be an electron donating group. So this would be for electron donating group, and this would be for electron withdrawing group. So you have two different scenarios. If you only had one group, then it would be easy to figure out. Okay, ortho para is going to be shielded, ortho para is going to be de-shielded. Here meta is shielded, and here meta is de-shielded. We are going to combine them in one molecule. So there could be a push-pull, a push-me-pull-you effect here. All right, let's look at that. So here is a benzene, and you have a doublet, and both of them have 2 hydrogens, which means you're very symmetric. Which one of these do you think can give you a very symmetric structure with just 2 types of hydrogens when you have 2 different groups here? Well, let's try this one and see how that goes. Okay, let's look at para disubstituted. Okay, this is more kind of explaining, you know, this pattern here, and trying to figure it out from all of these values. Now all 3 of them, 1, 2, and 3, would also have NH2 peaks, and typically they'll be somewhere, you know, below 6. So it'll be a broad singlet, and there'll be 2 hydrogens underneath it. The number of hydrogens for this is written on the top, so we don't have that integral going through. Over here we have 2 hydrogens, and let's suppose that this is going to be your structure where you have your NH2 and your nitro groups opposite each other. Would this give you 2 peaks or more? Let's look at it. So here you have your NH2 coming in, which is going to push these electrons over here. So that means you are going to have over here an ortho position that's got more electrons. than what we originally started with, and therefore you are going to get an increase in charge in the ortho position. Now let's figure out where else this can go. So this can then come down, and where there is no hydrogen here, so I'm going to draw the next structure. It's going to go all the way to the oxygen because its electron withdrawing is pulling it out. So you will have a resonance structure where your anion is now going to be on the oxygen, which is really very good. So the neutral one is the best, and this would probably be your second best. So here are your pi electrons that are running around. Now they are on oxygens. What else can we do? We can bring these back and dump them here, which means you would have over here an anion on the other side of the ortho. Got back your pi bond, and you have new pi bonds here, and that would be your electrons. So basically we have electron density increase on alpha positions here and here. So let's label these hydrogens as HA and HB. So there are 4 hydrogens here. My question is, which one do you think is A and B? Is this A or is this A? Or which one do you think, looking at these values? Yeah, we talked about it. More electron density would be shielded. Therefore, this would have a lower value than this. So this is going to be your HB. And since you have a symmetry here, plane of symmetry, this is exactly the same as this. In terms of de-shielding and shielding, you would get the exact same value for that. And this is going to be more de-shielded because we haven't dumped any electron density here. And so this is going to be the one that's more de-shielded. So ortho, para are shielded. Meta is de-shielded. You could also think of this as, let's say I didn't start at the nitrogen here, I started over here. Let's say I pull this out, you can see that this is going to be depleted of electrons. So ortho to the nitro and para to the nitro would be depleted. So that also reinforces this chemical shift value close to 8, which is very de-shielded. You know, when you had regular benzene, it was about 7.1. But now you have a very electron withdrawing group. It's going to get very de-shielded close to 8. And you can see how when you're ortho to a nitro group, you're going to be very de-shielded. So HA, without a doubt, is the one that's de-shielded, and the ortho para would be shielded. So that kind of explains chemical shift values. Let's look at coupling constants and, well, the coupling pattern. What are they going to look like? As we said, if you are right next door, you'll have the largest coupling constants because, you know, the spins here can interact a lot better. Also, 180 degrees or 0 degrees from each other, that would give you the maximum coupling constant value. If you're 90 degrees, the hydrogens are 90 degrees, that would give you the minimum value. So therefore, this is going to be pretty high. Let's say you have an electron withdrawing group. I'm just going to put NH2 and NO2 now. And you have 2 hydrogens here, HB and HA. Now HA and HB will couple and you would get a JAB. This is a 3-bond coupling, JAB, about 7 to 10. Okay, let's say approximately about 8. Let's say there was no other protons, HB would have just got 1 peak. However, HA is going to split that by 7 to 10 JAB coupling, 7 to 10 hertz. Now, do we see anybody else coupling? What about this proton here? This is para, and para is 0 to 1. And in this low resolution spectrum, you're not going to see this. How about this B, HB? Well, this is HB and this is also an HB. However, they can couple with each other, and this can split this into another doublet. So the larger coupling constant is the one that's going to split it first, and then you'll have the smaller coupling constant, in this case 1 to 3 hertz. So if you had a very high resolution spectra, you would see maybe a doublet of a doublet, and if they emerge, you would see a triplet. But for right now, we are going to look at only coupling constants above 5. So that means we're just going to look at ortho coupling, because that's what I've drawn here. But so that would be a doublet in a low resolution. If you had a very high resolution NMR machine, you could get a doublet of a doublet. So I'll put high resolution, doublet of a doublet. This is going to be JBB, and that doesn't sound well, so I'm going to put B1 here and B2 here. So that's going to be B1, B2. So if you had high resolution NMR, you would see a doublet of a doublet. Now if you go to the NIST webpage, nist.gov, and type in the name of a molecule, it would bring up a spectra, and you would see these values there. And they also have spectra for most molecules that you're familiar with. So what about HA? Who's going to split HA? Let's look at HA. So HA, let's say there were no hydrogens in the neighborhood, would give you a singlet. However, you have an HB that is ortho to that. So therefore, you are going to couple HA with HB1 first. Now that's going to give you a doublet. So if it's a low resolution, you would see just a doublet. So this is going to be your JAB coupling. However, even HA1 has got a meta proton. So this is going to be a 1, 2, 3, 4 bond coupling. All right. And you would see that here as well. So you would see a very similar splitting pattern here for both protons, because they pretty much have the same number and type of neighbors. So high resolution would give you a doublet of a doublet. So let's look at spectra number 2 and see which one of these is it going to be, meta or ortho. Both of them have 4 peaks. Since there is no symmetry here, each of these protons will have its own individual peak. Therefore, you would get 4 protons and 4 different peaks. And we have 4 different peaks here. So just counting the peaks, you cannot say whether it's ortho or meta. For para, you can. You typically have only 2 peaks. Sometimes those peaks can collapse, and you could have like a doublet of a doublet like this. That's very close. It almost looks like a huge peak in the middle with 2 tiny side peaks. So it depends on the shielding and the de-shielding and what groups. If they are very similar groups, then these can merge. Right? Let's look at this one. Let's try, well, para's out of the way. Let's try ortho. Let's see whether that works out for this. So if you have a ortho substituted benzene, that means you have a 1,2 substituted benzene. You would have an electron withdrawing group and an electron donor group that are right next to each other. So you have a NO2 here, and an NH2 group here. And we talked about what would happen with resonance. The NH2 group is going to put the electron density ortho and para to this molecule. So that is going to be, if you do that, this has got too many, it's going to push that out. And ortho and para positions are going to be shielded again. So here you would have your NH2 now become a positive because you lost the lone pair, and that's a positive. And you would have this electron then traveling around. So over here, it goes over here. You already have 4 bonds, so you got to pop something out, and that would be your pi bond. and that is going to then give you an anion in the para position. Now, if you have your NO2 group, sorry, is going to be here. And you can take these anions and travel around the ring, see the world. Well, in this case, there's no hydrogen, so I'm not going to put it here. I'm just going to put it all the way here. And that is going to give you a negative charge on just the ortho and para positions only, not on the meta to the amine group. So this is probably one of the most stable ones because your anions are on electronegative atoms, and you know Lewis structures prefer anions to be on negative atoms. So this is probably the second best. This would be the best. Now over here, ortho and para positions are shielded. This is ortho and this is para because the negative charge kind of tends to concentrate here on its way around the ring. What about the nitro? Is it going to have any effect? Let's draw it out. Let's start the resonance structure with just the nitro group this time and see where it's going to direct the electron density in the ring. The ring electron density would obviously affect the carbon electron density, which would affect the hydrogen electron density, and the hydrogen protons are what we are looking at here. If there are more electrons around the hydrogen, they'll be shielded and upfield. If there are less electrons or electrons are depleted, they will be downfield and have a delta value that's higher. And we know that. So let's look at what would happen if you just had NO2 group over here pulling out the electron density. So this time we're just going to start our resonance with the NO2. Obviously, it doesn't really stop at each one of these stations. It's just a description of the electron pathway or flow inside the molecule. So we'll flip this out here because the oxygen's electron negative, and we will put our electron density mostly on the oxygen that's next to the nitrogen. So you'll have a negative, negative, positive with a double bond. You would have over here a positive charge just because you pulled electrons out of it. So you can see that these positions are going to be very de-shielded. So if I were to number this as 1, 2, 3, 4, 5, 6, you could say that 2, 4, 6 would be shielded. And over here, you could say, well, 3, and now when you flip this over and put a positive charge, 3 and 5 are going to be de-shielded. So this is a very nice clear-cut case. So you have a positive here. And then you could, well, continue the resonance, and I'm not going to write all of them down. I just wanted to show you that 3 and 5 are de-shielded. 3, 5, de-shielded. Now on 2, there is already a substituent. There is no hydrogen. So we only have to look at the hydrogens on 3, 4, 5, and 6. Which one is which? So 2, 4, 6 are shielded, 3, 5 de-shielded. Hit that pause button, figure out these peaks before we come back. All right, so over here, if you have done so, let's look at this. So over here, you would have these two being these and 3, 5 being these. Now which one is 3 and which one is 5? If you look at this structure, in addition to having a positive charge, it is also having a very electron withdrawing effect through inductive effect, because you have a positive nitrogen here. And you can see how that's going to really affect the electron density here. So this is even more d-shielded than this. So you could say 3 more than 5. So I would expect this to be 3 and this to be 5. So this is your 3 proton, this is your 5 proton. Now let's look at the other ones over here. Which one is more shielded? Is it going to be the 4 proton or the 6 proton? So if you take the structure, we said 3 is more than 5. So that is the 3 is going to be the most d-shielded. Therefore, that let's label that A. 5 is going to be the next most d-shielded. Therefore, let's label that B, since we already have the values for it written over here. When you're talking about shielding here, which one is going to be the most d-shielded and which one is going to be the most shielded of the 4 and 6 CHs or carbons here? Which one's going to have more electron density? If you take this structure here, the anion is further away from the nitro and the iminium ions, whereas this one is closer to them. So this one is going to be more shielded than this. So this would be the most shielded, let's call that D, and this would be the one before that. So now that we've figured out all of these hydrogens, let's figure out if the coupling pattern doublet, triplet makes sense for this. Let's look at the splitting patterns for this. HA has one neighbor that's ortho, with a big coupling constant, 7 to 10 Hertz. So you are definitely going to see a splitting on HA due to HD. So if you, let's say HA didn't have any neighbors, it's going to have one peak. However, it does have neighbors. It's going to be split by the closest one with the largest coupling constant first. And so this is going to be JAD, 7 to 10 Hertz. Then it's going to have a smaller splitting due to the meta here. So over here, if you had a very powerful NMR machine, you would see the JAB coupling. So you would see a doublet on a low resolution, and you would see a doublet of a doublet on a high resolution. I'm just going to put high for that, okay, doublet of a doublet. This is a low resolution, so you kind of see a doublet here. Let's look at the next one, B, HB. Does that make sense? So if you put HB here, HB is going to be split by HD and HC. Now they are both in different environments. So let's say HB has no neighbors, you're going to get one single peak for that. However, it has neighbors, you got HC and HD, two of them in the ortho position. So you could say that would be a triplet, or you could, I could write it down like that, JBD, let's say, and then JCD, and this is going to kind of merge, and you would get a doublet of a doublet, because the coupling constants are close, you would get a triplet. Now all of these can be split by HA, and you could get fine lines here, doublet of a triplet. Okay, so I'm just going to leave it at that. I'm not going to draw it out, but I'm just going to say on a low resolution, you are going to get a triplet for HB. Does that make sense? Yeah, that's what we have over here. Let's move on to HC. HC has HB for the ortho coupling, 7 to 10 Hertz, and HD for the meta coupling, 1 to 3. You would rarely see this HA-HC coupling, which is 5 bonds away, 1, 2, 3, 4, 5. So let's do HC here, if you had HC and you really didn't have anybody next door, you get a single peak, but you do have HB here. So therefore, this is going to be a doublet on a low resolution, which is what you would expect. Let's look at HD. HD is in a very similar situation to HB. It's the same number of neighbors. So HD, if there were no neighbors, would get a singlet. However, it's got neighbors. So let's split it by, let's say, JAD. And the same amount of splitting or coupling constant here by the B proton. So that's going to be JBD. So the JBD is going to split that doublet into a triplet. So you would, on low resolution, see a triplet for it. Now, if you had a high resolution, each one of these is then going to be split into a doublet. So you might even see a doublet of a quartet if you're lucky, or a doublet of a triplet. Okay, so you have a doublet, triplet, doublet, triplet, and that's what you see. So for sure, this is the 1,2 ortho substituted. This was the para. And if you have electron donating groups and electron withdrawing groups in these positions, you could expect to see similar shifts and similar splitting. Let's look at how we can take these hydrogens here and assign them to these peaks. Let's look at resonance. That's what we've done before. Let's do it again. So let's take our nitrogen group and nitro group and see where they are going to dump those electrons around the ring or deplete them around the ring. Let's start with the NH2 group here, as we have done before. So you can have this come down here and put it over here, which means your ortho to the amino group is going to be more shielded. That's what you can see, say, from this piece of your resonance. Let's look at what this can do. So you can go around the ring and put it on the para position relative to the NH2. So your NH2 lone pairs are going to now end up para to the amino group. So amino group is dumping electron density on 2, 4 positions. Let's call this 1, 2, 3, 4, 5, 6. So 2, 4, and 6 shielded, because you can see how this can go around and put it on 6. 2, 4, 6 shielded. That's the conclusion we can come when we do the resonance with the nitrogen group. But it doesn't just do it one at a time. It's all doing it all of the time. We're just drawing separate diagrams to see what could be the possibilities. Let's look at your nitrogen on your nitro group here and see what can happen with the resonance using the nitro group. So your pi bond here is itching to pop up there and pull this in. And so therefore you would get a positive charge ortho to your nitro group. You can see on all of the structures, the sum total of the charge is 0, just like it should be, plus minus 0. 2 plus 2 minus 0. So this is going to be positive, and this is going to be positive when this comes down, and this is going to be positive. So let's do that again. So here you could do the same thing again. Bring this down and put your positive here, and you would have a resonance structure over here. Then you can travel one more time over here and do the same thing. And let's draw the very last one here and tell me which positions now are having the positive and which ones are having the same. Let's look at it. Squishing that in there. Which ones? Well, 2 and 4 and 6. So this is not clear cut at all like your para and ortho. The NH2 is putting electron density on 2, 4 and 6. NO2 is putting positive on 2, 4 and 6. So we could say with the NO2, 2, 4, 6 would be D-shielded. All right, so well, then what about these 4 peaks? They are not all at the same position. Now that we've drawn our resonance structures, let's go in and see which ones are these. Let's label them A, B, C, and D. A is a doublet, B is a singlet, C is a triplet, and D is a doublet in low resolution. In higher resolution, each one of these is going to have fine splittings. But let's do the major ones here. So which one is going to be the most D-shielded? We know that the nitro group has got a positively charged nitrogen and a pi bond, and this is the most electron withdrawing. And we cannot actually assign plus and minus to different carbons using resonance, so we're going to use inductive effect. So if this is pulling electrons out, well, you can see this is going to be very D-shielded. And so here, this is going to be your HA. Now over here, this is also ortho to the nitro, so you would expect that this would also have a similar D-shielding. Therefore, you would have that as your B. So that's your A and B. This is your electron withdrawing group. If you do inductive effect, then this is going to be your next most D-shielded, and this is furthest away from that, and that would be your D. Here also the nitrogen electron density is going to flow in here. So therefore you can say that this is going to be your C and this is going to be your D. Is that fitting with the splitting pattern? We are just going to do low resolution. As you can see, a very limited space here. So let's just do the ortho coupling. HA would have a neighbor that is on the very next carbon, HC, which is going to split that, and with a big coupling constant, about 8, JAC, and you would get a doublet, which is what we see. And each one of these has just one proton, which is why you see 1 written on top of each of those peaks. Let's move on to B. B really has no ortho proton. So if you have HB here, you would get just a singlet. But if you have a higher resolution, you would see a doublet of a doublet. It could be split into a doublet of a doublet if you have a higher resolution. Okay? High resolution. It's the same with A. HA can be split into a doublet of a doublet by HD and HB. Let's look at HC. As we can see here, HC was one of the ones that didn't really have a positive or a negative on any one of those. Now again, this is a resonance donor. This is a resonance withdrawer. So it pulls electrons off with resonance, that is literally pulling electrons from the ring. And it's also an inductive withdrawal, which means it's pulling electrons along the sigma bonds here and polarizing it towards this very electronegative group. So I'm just going to write here resonance and inductive withdrawal. Let's look at HC, the splitting pattern for HC. So if HC had no neighbors, it would get a singlet. However, it has 2 ortho neighbors, so it can be split by this, and they probably would have very similar coupling constants. Let's say JAC by HA, and then it's going to be split by HD. So you would have a splitting of those 2 peaks by this HD, so you would have a JCD here, coupling constant, and they would be almost equal here. So you would expect to see these two merging and giving you 3 peaks, which is a triplet. So we have A, B, and C taken care of. D is in a very similar situation here to all the other ortho protons here. Let's look at D. And if you take HD, there's a neighbor here right next door, which is HC. So it can have a JCD coupling here, and that would be a doublet. So you would expect to see a doublet, singlet, triplet, doublet on a low resolution NMR. And this is exactly what you see over here, doublet, singlet, triplet, doublet. So we can conclude very safely that this spectra corresponds to the meta substitution pattern. This one, without a doubt, corresponds to para. Paras typically have doublets or doublet of a doublet, and this one is going to have a splitting pattern that corresponds to ortho. So in summary, I'd like to say that these splitting patterns are going to be the same for ortho, meta, and para substitution compounds. Para will always be a doublet of a doublet, and ortho and meta would have these complicated splitting patterns. Now, ortho and meta splitting patterns are going to be similar just because they depend on the proximity of these protons, the neighboring protons. However, the delta values will change depending on the strength of the electron donator or the electron withdrawer groups that are on the benzene, the director groups. So if you have any questions, don't hesitate to ask me. This is a topic that you would probably understand better after you have thoroughly understood the chemistry of benzenes. I'm just leaving this here so you'd have a good understanding how splitting patterns work and de-shielding and shielding works in di-substituted benzenes. I will talk to you soon, guys, and let me know if you have any questions. Take a look at some of the problems in the book and, give me a holler if you can't solve them. Talk to you soon. Bye.